So today is the last class of part one of the feature engine section. Sorry, now the recording started. I deliberately repeated.
Okay, can I go?
Yes, go ahead.
Cool. I'm Mac. I'm going to talk about the VIF and coefficients. I didn't really get around to coding anything, but I just kind of have a conceptual explanation of what this is. We can come back to how it applies to our data in the end and talk about it more. What is the VIF? This is the variance inflation factor. It's a measure of the multicollinearity in our feature set. What's multicollinearity? Multicollinearity is similar to collinearity, but it involves correlation among 3 or more features, while collinearity involves only 2 features. Can you give an example to show the difference between these 3 terms? Yes. So some background. Correlation, we all basically know already. So on the left, we have strong positive correlation, in the middle, low correlation, and on the right, negative correlation. Collinearity, well, one guy defines it as just strong correlation, and he gives a benchmark of 0.7. He says that for him, anything above 0.7 magnitude, so it could be negative. Anything with a magnitude above 0.7 correlation is collinear. So we could read collinearity off our feature set heat map, and we can find out which ones are collinear. For me, it raises the question of what does multicollinearity find out that isn't picked up by collinearity? And this guy linked here has a really good example with this smaller feature set. If we use a benchmark of 0.7 as the benchmark for collinearity, then in this feature set, there's no collinearity because none of these correlations surpass 0.7. But you can see the X5 column. This feature has kind of medium correlations with all the other features. And this means that it's kind of very multicollinear, while there's no pairwise collinearity. So in this case, we have multicollinearity, but not collinearity. And this is what the VIF will pick up. What are the problems caused by multicollinearity? It really just has two serious problems. It will cause our coefficients in the model to have high variability, and the p-values associated with each feature will be unreliable, so that we won't know which of those multicollinear features is actually affecting the target. But interestingly, it doesn't actually have an effect on the prediction, and we can essentially ignore it. We could if we wanted to, and not worry about the predictive ability of our model. How can we resolve multicollinearity? We can just remove columns. We can calculate VIF for each feature, and we can remove the worst performing column, the most multicollinear. We can combine the problematic columns to reduce VIF. We can apply PCA, which is a different thing that someone else is going to talk about. A different technique. We could apply principal component analysis. And finally, we could just do nothing because, like I said, it doesn't affect the model's predictive ability. Also, if only certain features are multicollinear and we do want to have good p-values for others, we can ignore it then too, because it'll only mess with the p-values for the multicollinear features. So how is it calculated? We calculate a VIF for each feature based on the regression between it and all the other features. So we calculate an R² between one feature and all the others. So for an R² that varies from 0 to 1, or perfectly uncorrelated to perfectly correlated, we'll calculate a VIF that ranges from 1 or no correlation at all to infinity for perfectly explained or perfectly correlated with some of the other features. it varies depending what's the benchmark for a very bad VIF. It varies depending on the project and the sector, but 5 or 10 are typically given as benchmarks. And if you find VIFs above those numbers, one or the other, typically that's when you want to go through either eliminating columns, eliminating features, or combining them to fix your VIF until it's reasonable. What are our VIF numbers? Let me share my browser. What are our VIF numbers? So we have a couple features here on the left that are just spoiling the scale, because actually, like, these are actually too big as well. So if we look at the numbers, we see that the average temperature and the heating degree days are kind of massively large, but that a lot of the data in the middle is also too high. And I think what we see is that the weather data is kind of massively multicollinear, and I guess that's something we might expect from, I don't know, our intuition. So I can show you what Rich did to reduce these numbers. Rich changed from starting with here. This is all scaled and encoded. So there's some 60 columns, 60 features. Rich will have to correct me if I'm wrong, but I think Rich threw away 24 columns corresponding with highs and lows per month. And then Rich averaged 12 monthly averages into 4 seasonal averages and gave us scale Q1 through Q4. Is that right, Rich?
That's correct, yeah. I dropped the min, dropped the max, and extrapolated the mean from the average temperature columns and put them into quarters. Original plan was seasonal, but I didn't think that would make much of a difference. It did slightly improve the overall VIF, and it reduced the dimensions of the data set quite significantly as well.
Sure. So with Rich's data here in this table, the high is now dropped to 5,000 or so. So it's a massive improvement. The question for me is where to go from here. If we had to go through, we would have to go through another round of this to reduce these if we wanted to reduce the VIF, right? Which we don't have to, but we could. And I'm not sure what we would do now. I think if we were being really careful, maybe we'd want to go with PCA or just ignore it if we don't want to monkey with our data. And if we look at this data and we wonder what do we do about like the bottom or the worst performing features, how do we combine these? I'm kind of at a loss for what to do with these. They're interesting ideas for how to combine columns. You can take Rich took averages. We could also multiply 2 columns together or add them, and I guess you have to think about what the column says and how it combines with another one to make that decision carefully. Thanks, Rich, by the way, for clearing up a couple points of confusion over my studies. That's all.
Superb. Thanks very much.
Sure.
Thank you. Sorry, I was on mute. Any questions, anyone?
So I have one question. Sure. So it was a really good presentation. Means it cleared out several confusions I had related to VIF, because VIF was kind of like a new thing when Rich introduced, and it was really great clearing out those confusions, multicollinearity, and what exactly it does and everything. My question is, you said that multicollinearity we try to reduce it, but it doesn't affect the model, right? So why is that? Why does it not affect the model? If it doesn't affect the model, sorry, if it doesn't affect the model, then what is the point of doing it?
It affects your model's explainability or interpretability. So you won't be able to explain which of those multicollinear features are actually affecting your target.
Okay.
But your model will still predict fine when you move on to test data.
Mm-hmm.
Why does it still predict well? I don't know.
Okay.
Yeah.
Sounds good. Thank you.
Any other question, anyone?
So I have a question like,
Sure.
if I say like the number, multicollinearity and collinearity, so whether, correct me if I'm wrong, so multicollinearity means the number which is coming out less than 0.7. Am I
No,
correct?
greater than 0.7 would be collinear.
And how about multicollinearity then?
Multicollinearity, it doesn't, there isn't really a number for correlation.
Okay.
It's the sum of the correlations that causes it. No one gave a benchmark for the sum of correlations though. But it's the sum of those correlations with all the other features that would cause multicollinearity.
Okay. All right. Thank you.
I have a question too. So if we have VIF number, all of our column or variable more than 15 or 20, what should we do? For our data set, we see our VIF number normally more than 200, 200, 100, I see based on the column you show us.
Yeah, you're asking what would you do next, right?
Yeah, exactly. It seems we have to remove most of the variable now because of the high VIF number.
I mean, I would say we do nothing, or at least not this way. I think Rich mentioned that typically we apply BAF for smaller data sets, but it's an interesting technique to look at. I think with this data set, I couldn't imagine wanting to do anything in here. I think you would end up sacrificing predictability at that point.
Yeah.
Granted, I don't have experience with this field really, so one of you guys wants to correct me here. But I would be tempted to say it would be most prudent to not continue further than what Rich has already done.
Okay.
Yeah, it's generally used. I've used it on a smaller data sets where you can afford to mix and drop columns and things like that, because our data set is, it had 60 different features. It's difficult to run through the process of eliminating them because all of them do seem to have a slight importance. So that's why VIF is probably best suited for your smaller data sets, where the other techniques that we used, like RFE and things like that, they're much better for our data set because it's quicker and it's more automated way of feature selection and reducing the complexity of the data set. But yeah, it's mainly used to improve the interpretability of your results. It doesn't affect the prediction because how can I put this in simple terms? Basically, each individual feature within the data set has a certain predictive power, and VIF regresses on each of these features individually. So it's a sum for the individual power. So even when they're all combined, it will still produce the same predictions, if you understand what I'm saying.
Yeah.
It's quite hard to show you without the mathematical formula for it, but I'll write something with the maths in it that explains why it doesn't really affect the predictability.
So how about doing kind of feature important first and know what variable are so important and what variable are not, then do VIF? then we can kind of figure out which variable, if we remove it, is not going to affect our data set.
Yeah, absolutely. You don't have to do it first. You can do it near the end once you've picked you've selected your main features. I just put it in there because it's just one that is it's good to know, and it was just the first option I put in there. There's no thought behind the order of the VIF and where it is in the notebook.
Okay.
Any other question, anyone? Otherwise, we should keep going. Okay, who's next? Next is Manessa.
Oh, hey, Emma. Hey, guys. So let me share my screen.
Sure.
Let me know when you guys see my presentation.
I can see it.
Yep.
I think we can see.
Okay.
Yes. Go ahead.
Light show. Do you guys see it?
Yes.
Okay. Yeah. So let me start off with like, why do we need tree-based models for feature importance or feature engineering? So the main thing why we would be using tree-based model in order to find the feature importance is one is in order to find insights into the data set itself, insight into the model, and improve the already built predictive model. So in the data set, what happens is there'll be, so suppose we have a large data set, and we need to understand like which of the which of the feature in the data set is important for the target variable, so for the target where we are predicting. So in order to find that, like tree-based models is really helpful in order to find the appropriate features that is required for our or is associated with our target variable, or which is making a difference. And the second thing is the model itself. So in order to like optimize your model, so if you have like too many features in your data set which is not even important for your prediction, then that is of no use. So you can actually eliminate. So for model and more predicting the model, so it actually plays a vital role in order to eliminate the features which has least importance. So basically all these tree-based models, like it will give you a score in order to associate it with each feature in order to understand whether that feature, what is the role that feature plays for predicting your target variable. So let me explain. So I'm not sure like if everybody is familiar with tree-based model. So let me explain. So what exactly is a tree-based model? So tree-based model, so it uses a series of conditional statements, as you can see in this picture. So it uses conditional statements, a lot of conditions in order to like form a decision tree or form a tree basically. So that is a tree-based model. And so one of the the decision tree is like a vital part of the tree-based model. So what it does is, so as you all know, like we have both supervised and unsupervised learning. So decision tree model is a type of supervised learning, so which actually visually represents all the relationship between the features and the conditions. And it basically represents the entire data set in a conditional form, in a if-else way of format. So here you can see, so it's like a small data set for our example to understand. So suppose like we are dealing with a data set where there is a lot of people and we have age and how much they are spending. So our target variable is whether to determine, so whether that person is a high spender or a low spender. So you can see like we have age, and that we are again dividing it into whether that person is falls under less than equal to 40 or greater than 40, and whether he has kids or what is his spending limit for a week or so. So this is how a decision tree looks like. And in order to understand like how the decision tree is formed, we need to understand important terminologies associated with a decision tree. So if you say root node, So root node is actually the node which actually represents your entire population or sample. So based on the root node, we can actually go on splitting further. So it acts like a parent node, and it is like the topmost node in your decision tree. And what do you mean by splitting? So splitting is nothing but so whenever you have a node, it goes on splitting. So in our previous diagram, you can see, so age is one of the, here age is the root node. So it's like a parent node. So it is being split whether that person has kids or it has spending limits. So the process of dividing that further into different nodes, subnodes, is called splitting. And what is a decision node? So decision node is a subnode of whatever root node is, or any condition which is being split. So that is a decision node. And leaf or a terminal node is the finalmost node, so where it cannot be split. So it is the last node, it can never be split again. So similar to this, so high spender, so it cannot be split further into like different nodes. And what do you mean by pruning? Pruning is exactly opposite to your splitting. So where you'll try to remove certain subtree or certain nodes based on your decision whether that is important or not for your prediction. And branch or subtree, sorry, branch or subtree is similar to this. So it has a node and it has two subnodes. So this is called a branch. So it is branching out of your root node. And what do you mean by parent and a child? So parent node is root node. I mean, like it can be any node. So it depends on what part of the decision tree you're looking at. So suppose if you're looking at this part of the decision tree, then this would become your parent node, and the two terminal nodes will be the child node of this decision node. So if you consider this, so root node would be the parent node, and the two decision node would be the child node, and so on and so forth. And if you can see, so this is like a small data set which explains why I took this example is because ours is a big data set, so it is hard for us to visualize. So I'll come to explaining that part like a little later. So this we have like 4 features and 1 target. So where this is a data set where whether we can play tennis or not based on certain climatic conditions. So we have temperature as one of the features, which has like different categories in it. And outlook is one of the categorical features, and humidity. So it's one of the numerical features, and whether the specific day is windy or not. So this is a very simple data set to understand. So when you look at this diagram, so we'll know like how the entire data set is split up into a decision tree based on different conditionals here. So when you see this diagram, so you'll always have a question. So on what basis are we going to pick up the root node? So how the splitting actually happens? So for that, we have like 3 different categories based on which we are going to split our decision tree. So one is entropy, one is gene impurity, and one is information gain. So when you say entropy, so this is nothing but you are actually measuring like the different randomness in your data, basically your impurity in your data. So here I'm not going deeper into the mathematical intuition of how these formulas were derived. I'm just going to tell like why these are important for our decision tree, and in order to understand like how each of the algorithms that we have used work. So that's the reason I'm like giving you a little bit insights about all these concepts. So entropy has a formula where you are finding the probability of like each of these outputs. So if you go to the previous slide, so we have like number of yeses is 10 and number of no's is 4. So you calculate the entropy based on this formula. So the higher the entropy, it is bad for our split. So the lower the entropy, it is actually good for our split, and we can consider that particular node or that particular feature for splitting. And Gini impurity is another measure of feature importance as well. So here, all you're doing is you're actually subtracting all the summation of all your probabilities in your feature and your categories by 1. So if here you can see, is this diagram, are these diagrams clear? Like, are the numericals clear?
No, not really. I mean, it could get better.
Uh,
How about, can you deactivate that slide, next slide thing? So maybe this will enlarge it, this particular slide.
Which one should I do?
I don't know. Can
I
others
think-
see also next slide
yes.
option on the present on the
Yes, I think she has a presenter mode on. There are modes. Maybe go to display setting at the top.
Here?
At the top, on the top taskbar, go to display settings.
In the PPT itself, or in the Zoom? Oh, here, display settings. Got it.
Yes. Swap presenter view with the slideshow. Yeah.
Oh, okay.
Yes.
There it is.
Great.
Okay,
Thank you.
perfect. Thanks, Arma. Yeah. So
Yes.
now are these clear?
Much better. Yes. Perfect.
Okay.
Is it clear, everyone?
Yes.
Right?
Yes, it's better now.
Yes. much better. Thank you.
Okay, cool. Thanks, guys. Yeah. So here you can
Hey,
see,
sorry
like,
to interrupt. I think I don't want this meeting to be ended while she's explaining. How about we rejoin the meeting because it's a meeting about to end.
okay, sure.
Right.
I can rejoin.
Thank you. Yes, you can go ahead.
Sir, I have a question.
Sure.
Can you explain about the entropy in one word, like again, because
it is nothing but like how much of randomness your particular data has. So
randomness,
suppose,
okay.
yeah. So suppose if you're not able to find any particular patterns or anything, so that means that it has high entropy at that point.
Okay, so high entropy is like a lot of randomness.
Yes, a lot of randomness. That's right.
Okay.
Yeah.
Okay.
Yeah. So in Gini impurity, so what happens is all you're doing is, like, as the formula suggests, you are just subtracting the summation of all your probabilities of all your variables, what you calculate, by 1. So you're subtracting that by 1. So that gives you a value between 0 and 0.5. So 0.5 being the worst Gini impurity, Gini index, and 0 being your the best, basically, like, that can, so what happens is, so Gini impurity, where when you're splitting your decision tree, so you can, for example, you can take, like, playing tennis, outlook is equal to sunny. So you can see the small table where you have, like, whenever the days are sunny, you can see that the target variable where the tennis is played is 3, and it's not played as 2. So out of the 5 outcomes of the sunny. So you actually calculate those for each and every row in this data set. And you actually also calculate for the entire data set for the total value as well. So you can see, for example, in your outlook is equal to overcast and play tennis. So here you can see that your Gini impurity value or Gini index value is 0. So why it is 0? It's because it's your the split is pure here. So when you visualize it as a diagram, so you have like overcast at the top, and yes and no, like it has its child nodes, and it has like 4 yes and 0 no's. So here 4 yes, so that cannot be further split up into anything. So that's you can that's the reason you can think that is one of the best case scenarios. You can start splitting up using the outlook is equal to overcast for that particular subtree. So make sense? So 0.5 is the worst value for Gini index, and 0 is the best case scenario for splitting. So the least the value, that is what you use for splitting the node. Information gain is another form where it is also used for your splitting of your decision tree, and how you actually pick up the root node. So here entropy is like it's nothing but like information gain. It's entropy of one particular outcome minus your entirety. So you can see that like I'm actually not able to see this, but okay, there. Yeah. So here it's nothing but it's the decrease or increase in your entropy value. That's how the information gain is calculated. So here you can see that Outlook has an entropy of 0.693, and you can see that here the entropy of the entire target variable is 0.84. So if you subtract that 0.84 minus 0.693, you can actually get the entropy of playing tennis in Outlook. So the higher the value of information gain, the better is for your splitting. So the lower it is, and it's not good for it. So it is vice versa for entropy here. So these are the main things that we should understand, like in order to understand different algorithms with respect to the tree-based models. Okay, so when you visualize the tree-based model, this is how it looks like. So here the splitting is done based on the Gini impurity or the Gini index. So okay, this is yeah. So the another thing we need to understand is like how are the tree-based algorithms like divided. So there is something called ensemble methods. Ensemble method is nothing but combining multiple models in order to produce better predictive performance of a model. So here it's divided into two different ensemble methods. One is simple ensemble method and one is the advanced. So I'm not going to concentrate more on the simple ensemble methods because we have in our case, in our data set, we have implemented the advanced ensemble methods. But I'll still like define what these I'll just tell on a high level how the simple ensemble methods work. So max voting is nothing but you actually pick up like the number of votes. So suppose if you are voting or you are rating some restaurant, so you are rating 4 or 5 for a restaurant, 4 or 5 being the highest and 4 being a little lesser than that. So you actually calculate, suppose there are 5 people who rated a restaurant, and among 4 people rated 4. So in that case, you'll take like maximum number of voting. So 4 being the maximum number of voting, so that would be picked up. So in averaging, you actually pick up, you will just take the average of all the votes, that is all the ratings that is being there, and you will divide it by the number of people who actually rated the restaurant. So weighted average is where you will actually add some weights. You'll pick up some weights, multiply that with that rating or ratings provided by the people, and then you divide it. So it is an actually extended version of averaging technique. The advanced one is we have stacking, bagging, and boosting. So in our case, we have done like implemented bagging and boosting technique mostly, which like the algorithms that follows the boosting technique and bagging technique. But I'll still like go through stacking as well. So this is one of the very good diagrams I got to explain what these advanced ensemble techniques mean.
Nice.
So here we actually take the entire data set. We'll start splitting into sample data. So it can be different samples as well, and it can be like combination of one sample and like first sample and second sample. Combination of that can make a third sample. So it can be like random. So you'll randomly sample your data here, and you will split up into like smaller data sets, and you'll start like feeding it to different models. So you can see here, one of the sample data set is going to KNN algorithm, and the second one is going to decision tree, and the third sample is going to a support vector machine. So here you will take the outcome of all three, and you will, if it is a classification, you will go through the voting technique or the averaging technique. Max voting technique. And here, if it is a regression problem, then you will do an aggregation of that, and then you will compute the result based on that aggregation. In bagging technique, so it's again, you are like sampling out your original data set, and you are feeding it to different tree algorithms. So decision trees, basically these are decision trees. And you can see that it is being written as same algorithms. So for example, so bagging is used in random forest. So you will have different decision trees, and you feed all of those, and you will take the average of those results, and that would be your prediction outcome. So in boosting, it is slightly different. So you can see in stacking and bagging, it is sort of similar, where you are like just feeding into different models and you're just averaging. But here in boosting, it is slightly different. So you will have one single data set, like one sample of the data set from the original data. And then you will be feeding it to one tree, one specific tree. And from there, you will get a new, you'll get a new outcome. So that outcome need not be like a very good outcome. So in case if that outcome has a lot of errors, like if it is not predicted properly, so you will actually like penalize that particular thing, and whatever error is there, like you will start improvising in the next thing. So you will get a new data set from this, and you will actually penalize those features, whatever was not giving the right output, and then again you will feed it into the data set. So here it is like parallel, here it is sequential. So you will have like lot of weak learners, which will at the end make them a strong learner or a strong predictive model. So you will keep repeating, or you keep adding new trees and new data sets, like based on the previous error, you will be fixing it into the next tree or whatever next model, and you keep repeating until your model is good enough. And in our case, like, so the different algorithms that we used were in order to predict was one is bagging technique. So one is random forest and decision tree bagging. So this particular topic will be covered by Masood. So I'm not going to concentrate on this particular part of it. So I'll be concentrating on gradient boosting machine and XGBoost and light GBM, whichever we have used in our feature engineering process. So in gradient boosting, so it follows the boosting technique. So you will have predictions from multiple decision tree to generate the final outcome prediction. So we have, this is the base of both of these algorithms. So gradient boosting machine is base for both extreme gradient boosting machine and light GBM. So the difference between light GBM and extreme gradient boosting is in extreme gradient boosting, we do the level-wise splitting. Like you can see that it's like vertical level-wise splitting. But in light GBM, you see it's a leaf-wise splitting of the decision trees. So you can see like you keep adding new leaves, and it's like it's one single node that keeps getting added. Here it will be the level. So it will be the entire row that gets added. Here it is like one particular data point that gets added. So let me share. Yes. So here you can see that in our case, we are using yeah, we are using XGBoost and LightBoost both. First, sorry guys, I just lost track of where it was. Yeah, let me start off with light gradient boosting. So it uses the boosting technique. So it is called light because it has better performance and it performs better than XGBoost. So here we are importing light GBM library. So it has in our case, we have to use a regressor because it's a regression problem. And you'll actually split up your data into X-train and Y-train, and you feed it into the your light GBM regressor. So here, all you're doing is you're creating an instance of that, and you're actually calling a fit method on that. So what this does it will fit your data set into the light GBM regressor model. I'm not going to touch on these because these are the prediction metrics that we would be using. Probably this would make more sense once we start building the model. So because this is not required at this point in time, so I'm just skipping this. So we are plotting the importance of each and every feature in our data set. So you can see that scale floor area like has the highest score, like feature importance score, and a day scale days below 20F that has the lowest score. So this gives you a very high level of like which feature is important for your model predictions. And we have our XGBoost. So in XGBoost, we use Gini. You can see here, like purity index. You use Gini index as for splitting your decision tree, basically. And yeah. So we are importing your XGB regressor from XGBoost package. So you're again creating the instance of that, and you're fitting your model, and you get what is the importance of each and everything. So here you can see scale heating degree days that has the highest feature importance score, and encode state data. Okay, so this is whatever this is a scaled feature, I guess. So you can see scale days above 90F has the least feature importance. What else I would wanted to say? Let me get back to sharing my screen presentation again. Okay. So the last thing I wanted to show is I'll probably adding 2 more slides for the final, because I wanted to like take screenshot of what is done in our code. So I'll probably put those 2 screenshots before this. So this is one thing I found. So this is one of the things Imran shared, and also it's very good. Like if it's very easy and handy, and if you keep reading this every day, it's very important for your interview. So that's the reason I put this here. So it has all the tree-based model algorithms. Then it has description of what each of them does and their applications. That is the use cases where this particular algorithm can be applied. So in our case, like XGBoost, like churn prediction, claim processing, insurance, and stuff like that. And probably we can add, like we are also using on our our data set. So we can actually use even the weather data or climatic change data as well. And you can see the advantages and disadvantages with respect to each of the models. Yep, that's it. I'm good. Let me know if you guys have any questions.
Any questions, anyone? Please ask.
It was really good presentation, Manasa.
Definitely.
Thank you.
Yes.
Thank you so
So I have one question.
Yeah.
So, for example, you talked about Gini index and you talked about entropy and everything, because I know that there are, in which case classification or regression you use what? Means when do you use Gini impurity, or when do you use gain, or these impurity means do we have to use all of them, or we have to use them in specific cases?
Oh, that's a good question. So the example I have taken is with respect to classification problem here, but I think like we can use all of them even in case of regression as well. Because if you see XG boost, so it is using Gini impurity, right? But still ours is a regression problem. So we are not actually manually creating any of them, but XG boost algorithm, it automatically creates. So it automatically chooses like Gini impurity to like compute whatever it wants in the regressor as well.
Because I believe, I'm not sure, but I think Gini index is usually used for classification problems, and then entropy is used for the regression. So yes, it is kind of like a built-in background mechanism. If you use, for example, XGB regressor, it will automatically pick that particular maybe entropy. And if you are using XGB classifier, then it will pick the Gini impurity. So the formula is kind of like a bit different. I don't know why. That's why I asked that question. This is a confusion that I want to clarify myself. So I have not a good answer of why is that, but that was my question technically.
Yeah, even I'm not sure on that, Salman. Probably I'll have to research on that as well. Yeah, I'll probably get back to you on that for sure.
Yes, definitely, and I will read up on it, and if I get my hand on it before you, I will just share it.
Yeah, so, sure.
Yes,
yeah.
Yes.
Just one request: both of you share on a group, so at least other participants, if they
yes,
have
Imran, yeah.
Yes. Because I was reading about it, and this question kind of like means I did not get much time to spend on it. So once I spend it, yes, it will be we will be able to clarify what exactly, when to use which one and why exactly. But this is something which was going through my head because you started talking about it. I thought maybe you read it, maybe you went through that particular step, but that's absolutely fine. We can do that study later. Yeah.
It's a very good question, though. I was also thinking that when she was presenting. So yes, I think it's a good for us, all of us, to do our own research at the same time.
That was my whole point, to kind of like bring this question to the table so that everybody think about it. Yes.
Good one.
Sure, I'll get back to you for sure on that, Salman. Yeah.
Thank you, Manasa. That was a good presentation. Really good.
Yeah. Thank you.
Sorry, Imran. I didn't want to interrupt, but I have to leave in 1 or 2 minutes. I didn't even want to interrupt the Manasa too, because it was a great presentation. I didn't expect it took time for about 20 minutes. I thought it's 5 or 10 minutes each. So I think Manasa kind of, we had both same subject. I supposed to expect the random forest result, but she was too detailed with everything. It was a great presentation. I didn't have any new things. I had my presentation ready, but really I have to be in another meeting.
Okay, that's understandable. In that case, I don't know if you'll be comfortable. Like, is it okay that you just self-record yourself for 5 minutes and then you just share your recording of your part on our group chat later on, whenever you have time, later today?
Yes.
Okay, perfect.
Definitely.
That should. Thanks, Masood.
Sorry, guys. Sorry, I have to leave. Bye.
Sorry, Masood.
No problem. It was a great presentation. Really didn't want to interrupt you and tell you I don't have time. I said, okay, I'm learning. Thank you, guys. Bye.
No, good job, Manasa. I think it was good because there are many beginners, so it's important to assume like go in more deeper at the very foundational level. So that's totally worth the time for sure.
Yes, that was really good. Yeah.
Right.
Thank you. Thank you. And one other thing I want to stress on was, so if you want to really understand like entropy, gene-impurity, information gain, so that you don't want to forget. So I would say like solve like 1 or 2 steps
Yeah.
or problems like
Yes.
this.
Yes.
Mathematically, you will be very strong. So that's how I am learning data science and machine learning, because it's going to be inbuilt in your head. And like, so whenever you pick up an algorithm, you know what is happening in the background, because none of the algorithms actually shows you how exactly it is executing. So in order to understand the base behind how the execution happens or what exactly is happening in the background, it is good to do this, like since most of the algorithms are black box and it's very hard to understand. Yeah,
absolutely right. I totally agree with you. And I have seen a lot of people giving advice that you don't need to learn mathematics behind the models. That is wrong, because yes, for first time you're learning, you know how to code, that's good. But while tuning the model, you need to have a good understanding of the model, what the background working is, then you would be able to tune it way better. So
right.
all those people who are winning Kaggle competition or something, they know kind of like what things to tweak around in order to
Right.
get better results. And you would never know what things to tweak around and what exactly they can change, or they can kind of like influence the model or something. You need to understand the background mathematics. So my strategy is don't go all in just spend 1 year on mathematics only. Once you learn one model, then go deep down in that model, learn the
Right.
mathematics for only that model, and then apply it in several different situations. Then when you are good at that model, then move on to the next model. So
Right.
do it model by model. Yeah.
And the other thing is the problem, I mean, if you don't study the mathematics behind models, the problem where you'll start limping is during the hyperparameter tuning, because you don't know what parameters to be tuned. So it is better to know the formulas before and what each particular aspect in the formula does. That helps you like do the hyperparameter tuning very quickly and saves a lot of time.
Thanks a lot, Manessa, for sharing that your approach, and thanks, Salman. I agree with both of you. I think it's just to add on, maybe well, it should still help you guys. I recently had a one-on-one meeting with the director of data science in J&J, and he was saying when he hires in his team, he said he heavily emphasized candidates' understanding of the algorithm, like inside about the mathematics. So he said even he usually asks a candidate like, what's your favorite algorithm? And he keep asking about the deep, how much technical understanding, because they eventually have to write their own algorithms as well. So this is why there's also a good motivation that you should know why you're doing what you're doing. Okay, any other questions, anyone? Anyone, please ask. It's a good. Today's your last chance to ask in feature engineering. Can you go on slide 28, Manessa?
Yeah, sure.
So one thing, I have a question. I'm just curious.
Sure.
On this stacking thing. So yeah, it just picks it just goes through the data and goes through 3 different algorithms, and then whatever the outcome there is, it just funnels that in, and then based on that, you said it takes the average. What you said, I still have to watch.
So it depends on regression or a classification problem, Imran. So in case of a classification problem, it will pick up something which has a maximum voting. So in case of regression, it takes the weighted average or average in order to get that specific output.
Okay, that makes sense.
Yeah.
And can you give us an example? What algorithm is using stacking or boosting?
So boosting is used in XGBoost, right? Or LightGBM.
Yeah.
Stacking, so it's I have never used stacking before, so I'm really not sure on what problems it can be used. But yeah, so it has different algorithms. So all these two uses decision tree in specific, bagging and boosting mostly, but stacking
Yeah.
uses different algorithms. So it depends on the problem statement, like if this is appropriate for that specific problem, where you can use KNN or decision tree or SVM in mixture in order to get the output. But I'm really not sure of the use case for stacking.
So the use case is pretty simple. It's kind of like I have applied it in 2 of my projects. They were classification based. So what I was doing is the number of features was more than 100. And what I was doing is basically first I was using the logistic regression, and I was applying the penalty regularization, the lasso one. And based on that, it was giving me 63 features. So it was reducing the size of the features to 63. Then I tried the decision trees, and decision trees kind of like gave me a different feature selection. And then I applied. So it's stacking is basically combining several different models all together and then do the voting at the end. So it's kind of like that. Random forest is kind of like a stacking, but here it uses decision tree for every single model that it is training. But stacking is you can choose any particular model.
Yeah, and then you choose like the common features.
Yes.
Right.
Yes, and
it is.
And also it is similar to like trial and error. Like if you pick,
Absolutely.
you start off with one algorithm, you pick whatever like you feel suits best, and you'll go from there with different algorithms, and then see like whichever works better, and you take the average, or you pick up the max votes. Yeah.
Thank you.
Any other questions, anyone? Remember, when you ask any questions from someone, that it only helps you to make your concept more clear, and it mostly stays longer in your mind as well. So don't be shy, just ask. Nobody's going to judge anyone.
Even if you have questions around all of these, like you can like post it on chat, or you can ping me on chat as well in Slack.
Yes, and the idea for this project is so then all of us become comfortable once we are done with some Umdina project, because after we are done with Umdina project, and if we cannot execute every task of our own, well, then defeats the purpose to come on to the meetings anyways, right? We want to learn that skill. So this is why don't be shy, just ask. In fact, you made me more excited. There's a list. Oh, sorry. In fact, you made me excited. There's a list for that algorithm for DataCamp 1, which I shared. There's already bunch of algorithms. Perhaps it's good to get started with a different algorithms, mathematics, and then know for each. Well, that's something, my personal project. Any other questions, anyone? Otherwise, we're going to start. I'm going to create, I think we should rejoin the meeting, and then we should keep going now. I think time is running away. Let's rejoin, and then Tim will present.
Hello, do you hear me?
Hello.
Yes, we can hear you.
So should I start the presentation?
Can you guys hear him properly though? Isn't it too low, his voice, or no? It's only just me.
Yes, it's a bit low. It's difficult to hear, but I can still
now,
hear.
do you hear me more? Better?
How's everybody? It's low, right?
Yes, it's low. Sorry.
On chat as well, somebody also posted.
And now?
Much better.
Much better, yeah.
Okay, I just increased the volume. Sorry.
Sweet.
Okay, so can I start?
Well, I just got the game same. Hello, say something, please.
Hello.
So,
hi, Rich. Can everybody hear him?
No, I can't
Yep.
hear.
do you hear me now?
Yes.
No, it's like it has a lot of noise, I guess.
Yeah. So yes. Please advise him.
And now? Test one. I don't know, my micro is always going, it's decreasing the volume every time. have to call me back. Do you hear me?
I think it's going out of kind of like a lot of noise. When you say a bit louder, it creates a lot of noise.
Okay, maybe should I restart my PC, but it will go out of time. I'll try to restart it, okay?
That's a bit better. I'll check on your sound settings on your PC. Check the volume boost option on your sound settings, because it sounds like that's applied.
Okay, I'll just try to reboot the PC.
I've also just put a note in the Slack just about the correlation and why it doesn't affect prediction power. I found someone who explained it a lot better than I did. Just for clarification on that, if anyone was still confused about it.
Any questions, anyone? Okay. Hi Tim, what's the update? Sorry.
I think Tim's just started his computer.
Yeah, isn't it taking long? Okay, since majority of you are here, I can make some of the announcement at least, which is on my agenda. Just to update everyone, based on the poll results, our part 2 of this project will start from July 6th, which is Wednesday. And we'll be keeping same time. It will be 9 a.m. Eastern time. Right? Any questions, anyone? It's so basically it's a week kind of break from now. What I highly encourage everyone to, maybe if there's still some doubts, rewatch some of the recordings, because most of the stuff is already covered over there one way or the other. Either Rich covered, Salman covered, or other presenters covered. So to clarify the concepts, and maybe just read beforehand some of the stuff on model development stuff or model deployment related to part 2 stuff as well. Anything you would like to add, task leads, for the presenters, so then how they spend their week?
I think I would recommend looking into different models. Means start with the simple basic models: linear regression, lasso regression, elastic net, ridge regression. Means as Manasa in her presentation, she said that she emphasized that learning a little bit of mathematics would do a good deal. So I would recommend, instead of doing it at the end while making the presentation, start kind of like going into the mathematics of those basic models first, because all the models work exactly. If you understand linear regression and you learn about different penalties, L1 and L2 penalties, you would learn about all the remaining three: lasso, ridge, and elastic net, which means I would recommend you go and read about linear regression, then why we use regularization, and what kind of regularizations are there, what combinations you can use. Means by doing combination, you can use an elastic net. Similarly, then go and read about the tree-based methods. How does a simple tree? Manasa gave a very good presentation. Learn about it, because we would be applying all of those. So if you want to start from that, do that. Go and learn the basic model first, understand the basics of it, and then if you want to expand, you can go on the advanced models based on those models, like random forest, gradient boosting, stacking, or so many different things. I would recommend that.
I agree with that. And in terms of sort of really understand what we've done so far, I would even be, I'd probably think it was a good idea to see what we've already done up to the feature and try up to feature engineering and try it on a new data set. Just download a data set from Kaggle and try and re-implement the steps that we've done on a fresh data set. And that will show you whether you've understood each step of the way. Because it's easy when we've already got the data there, but if you try and then tackle the problems of a data set that you're not familiar with, it'll really drive home what we've done. And I think that'll be probably, if you need to go, if you're a bit unsure with any part of what we've done already, if you do that, I think that will probably be the most effective way of understanding what we've done.
Yes, that's a good point. Applying it in different situations. Yes, go find regression models. Kaggle is one thing you can go to. UCI machine learning have a lot of data sets. Go and find those data sets, and you can search using the term regression. It will give you just the models which are regression based. Scikit-learn has a built-in data set stored in it. You don't even have to go anywhere. You just call it from Scikit-learn. You just call the data sets and pull diabetes data or some different data sets from it. So try to apply all the steps on it, because any kind of a data that you are doing regression based things right now, since we have not gone into the regression part, the EDA part is pretty much similar. So apply it in different situations, and that would be a good point. Yeah.
I'll also share the link to the UCI machine learning repository. It's a good place where you can just download 3 data sets for a number of different problems, classification and regression. And generally the data sets in there aren't too complex. So it'll be a good one to start exploring, just to get a handle on what we've done so far and what we're going to do in the next phases.
Are they like clean data? Are they clean data sets, or?
Some of them are, some of them aren't.
Yes, some of them are, some of them are not. If you want to kind of like practice what we did, try to find a dirty data, because a lot of missing values, a lot of categorical variables where you need to try different imputation techniques, encoding techniques. So try to find that data and apply that. Yeah.
And I have one more question. What will be our problem statement, or what we're going to do next month?
I will. Sorry.
Yep.
Go ahead.
Yep. You go ahead, Imran.
I will share problem statement. It will be carry on from last time, but there's some models we have decided which we're gonna do more. I will update I will send in a day or two, so then you can read it.
Oh, okay. Sorry. Okay. I haven't sent it yet. Okay.
But generally, our goal is model development, hyperparameter tuning, evaluation, and picking the best model. Since we tried several different encoding and imputation techniques, we don't know which technique is going to give us the best results. So what we are going to do is we are going to train our base. First of all, try with the baseline model. After you have a baseline model, we will run through several different models, and we will pick 3 top best performing, and then we will hyperparameter tune them, and then we will kind of like evaluate them, and then we will try the different encoding techniques which gave us a different data, and then we will do exactly the same thing with that. Once we end up doing all the techniques and model evaluation for everything, whichever is giving us the best results, we will stick with that model. So that would be the strategy.
Okay, thank you very much. Okay.
Well, thanks Salman and Rich. I think that was good advices. I think Tim is saying he just need 2 more minutes.
Yeah.
That is one of them. Also, for part 2, actually, I wanted to just keep it open floor with all of you. Like, feel free if you guys, although I think we have already have a lot to cover, but feel free if you guys anything. I'll share the problem statement, read that, and if you think maybe we can add some more stuff or maybe remove some or whichever, put your more input as well. Maybe we can tailor it based on our group's need as well. Further. Well, while he's coming, I personally are looking, although I have my own notes, but there's some list I was curious. I hope there's a more structure on with supervised and unsupervised learning and different algorithms one can apply. There's one post I shared, Manisa quoted today, but I still, if somebody have anything better, please feel free to share. I would like to share something very quick. Maybe it might help to the beginners, especially. Let me share my screen very quick. Same one, not trying to show something which I shared. I know there are many better out there. So if somebody has better, please share. But as far as beginners are concerned, maybe they can read a little bit about some of the algorithms which Salman and Rich talked about, like linear regression, logistic, and just know more about it. So maybe in the meanwhile, when there's a 1 week break, maybe a beginners can maybe just read about these, more about these algorithms, and maybe watch some YouTube videos or some of the, for the data set, as Rich said, pick the data from UCI database and maybe play around with that as well. That's just a side thing. So that already has a bunch of different supervised and supervised learning techniques. It's a good, can be a good starting point. And if somebody has a better list where it all shows all algorithms, so please feel free to share as well. Okay, that was just a side thing. Tim has joined us.
Sorry, do you hear me now?
Hello.
Do you hear me?
That's better. Yeah.
Okay, I'll try to start. Okay, so so my part was to explain the principal component analysis. And it's my first presentation, and I will try to do my best. So I will try to explain why we need dimensionality reduction, what is PCA, principal component analysis, and how to use it in dataset. Just to double check, do you hear me well? Okay.
Yeah, not bad. Do you mind closing properties icon on your right? Or maybe switching to presentation mode? That would be better.
So which? Just 1 second. Now it's better?
Well, on the top right, there's a properties cross. You can just cross that out, maybe.
Sorry, I did not understand.
On the right hand side, you have a properties table open. If you can cross that out, that would make it bigger.
I have it.
Yes, this property is one.
Yes,
there's a cross. No. On the right side of the slide.
The right side of the slide.
Yes, at the top means at the top you can see properties written and dipole written.
Yeah.
Okay, it's okay. I think we should get started. It's already 9:50. So we need to wrap up.
Yeah, just
Okay,
just
It's okay.
I think that's fine. Yeah,
It's fine. We can see it. Go ahead,
so
please.
the main idea of the best way to visualize the data set in your mind is to imagine that every row is a point and the column is a dimension. If we have two columns in a data set, we can easily visualize the data set where each column is an axis. We can go further up to 3 dimensions, but more than this, we just can't imagine our visualized in space. In our dataset, we have 69 columns. That means it's space with 69 dimensions. First aspect is to reduce the dimension of the dataset without losing the relationship.
Sorry to interrupt. I just want to make sure if we are on the same page. Are you presenting slide 19, or you meant to show something else?
No, I'm 18.
Why does it show different on my screen? Which slide is everybody seeing?
19.
I see 19.
Yeah, it says thank you. Stay in touch on slide. So I just want to make sure we're on the same. Click on 18.
I just 1 second. Okay, do you see it now?
Yes. Can everybody see it?
Yeah, that's better.
Okay, so the main idea is to show that our data set.
I think you meant to start from slide 17. I at least I didn't see it. Did everybody see slide 17? I think that's where you wanted to start, right?
Yeah.
Okay, go ahead, please.
So why we need to reduce the dimensionality and how we're gonna proceed. So I will start from the beginning. The best way to understand a data set is imagine that each row is a point and every column is a dimension. For example, our brain can imagine a 3D dimensional space, but we cannot imagine something like more than 3 dimensional, like 4 dimensional. We cannot visualize it anymore. In our actual data set, we have 69 columns initial, and it's really impossible for our brain or to imagine how does it looks like 69 dimensional space. So we will try to reduce it, and this is a dipole schema that can just make better understanding. So this is each point it's a row. So now we need to reduce this to have a better idea and to improve how our model will work with data without lose the relationship between each point. So we can reduce it in a 2-dimensional space or in a 1-dimensional space. So how can create a PCA algorithm? So it can be thought as a projection method where data with m columns features is projected into subspace with m or fewer columns, where it retains the essence of the original data. So I will try to show it in our. So the first step is to calculate the mean value of each column. So it's how we can do it by from the beginning. Then descend to the values in each column and subtracting the mean column value. The next step is to calculate the covariance matrix of the centered matrix. Correlation is normalized measure of the amount and direction, positive or negative. The two columns change together. Covariance is a generalized and unnormalized version of correlation across multiple columns. A covariance matrix is a calculation of covariance of a given matrix with a covariance scores for every column with every other column itself. So to have a better idea, this is this dipole, when we can understand that the rejection just a projection on one of the axes, and we have the idea of the correlation in one space. So now I will move on the code to understand better how it works. So do you see my code?
Yep.
Sorry, everything closed when I shut down the PC. So I'll just explain the code that Rich used in the. So it's this code of the project. So now I just used the data set after we ended the data cleaning and the data analysis part. And now we'll use the algorithm provided by scikit-learn. So scikit-learn provide a PCA algorithm that we can use directly. So without any without build it by itself. So we have created to understand how many dimensions we should reduce our space. And after we know that we reduce that of 43 dimensions, we drop to 10 dimensions. And now we have 10 new features, but you have to understand when we use PCA, we are not using 10 features of the data set. We are creating new 10 features correlated with each other. And the first one is the most correlated, and it's like decreasing shortly. We can see it in this diagram, histogram that I did. So you see the first column is the one more correlated with each other, and then we see that's decreasing very soon. So to understand the shape of the of the data set is that we pass from 43 rows to 43 columns to 10 columns. And this is how does it look. So we have to understand that all columns here does not represent any features that we had previously. It's something new that we can use now in a new model. This is for the PCA. For the RFE, I jump back into the for the presentation. So recursive feature elimination, or RFE for short, is popular feature selection algorithm. So this algorithm is used for random forest, and it's try to improve and find the best features that we can select, and the most useful one is such as I understood is if I'm not wrong. So every few works by RFE works by searching for a subset of features by starting with all features in the training data set and successfully removing features until the desired numbers remains. This is achieved by fitting the given machine learning algorithm used in the core of the model, ranking features by importance, discarding the last importance features, and refitting the model. This process is repeated until a specific number of features remains. So I jump back to the code. So I will use the code that Rich made also. So regression for random forest. So here we will try, this part I'm trying to understand the best as I could, but it's not clear, but I will try to do my best to explain it. The main idea is to find which features and how many features of them will be the best to run in this model and give us the best result. So after we used our data set to train the train data set. We can see that the best scores are those one, and it's increasing the scores. So we use the cross validation. So we can see here. So the best results come with 20 features selected. So this will give us the best result for the random forest model. So sorry, I'm too bit stressed.
Okay.
So that's for me the presentation. So sorry for.
Oh, sorry for what? Thanks, Tim. No, good talk.
I'm just
for
a bit
sure.
stressed. So if you have any question, I'll try to answer.
Any questions, anyone, for Tim?
It was really good. I just want to clarify one thing. For example, this RFE, a recursive feature elimination, it can use any model inside it. It doesn't have to be just random forest. It can be any model which do feature selection as one of its features. But for example, all the tree models do feature selection in the background as built-in function into it. So we can use all of them up. For example, in this scenario, we can also use linear regression or lasso regression, because if we kind of like standardize our data, that means now every single feature is comparable to each other, because every single feature has a mean 0 and standard deviation 1, which means now if you run linear regression, it can do the it can calculate or train the coefficients. So based on whichever coefficient is the smallest, we can keep on dropping one coefficient at a time as well. That is what we can also do. You can use lasso regression, ridge regression. So there are so many different possibilities of base models that you can use using this RFE. I just wanted to clarify that. Yeah, good job, Tim. It was really good. Yeah.
Many thanks. Thank you very much for your explanations.
Thanks, Salman. Thanks, Tim.
Sorry for the beginner question, but PCA, I don't know. I tried to learn it like a few times, and I think like I basically not understand it properly and deep. What is it like exactly? How to calculate it in mathematical way? Do you have a good source where to train, or is it like so much calculation that we can do by ourselves?
Okay, the best thing that I found to understand mathematically this, I will show you the link. Is I guess
Great.
everyone knows this site is Machine Learning Mastery, and he gives. So I will send you the one where I made my searches. So he explained how you can calculate out of the box of scikit-learn and do it with NumPy. Do you have an idea with NumPy? So it will be much better and clear to understand for the beginning. Just with the PCA with scikit-learn, we can reproduce it much easier and faster than just create all function with NumPy. That will take more time, and it's not very very useful in a real data set. But for understanding, I will share you all the documentation in our Slack. So it explain with all details how you can implement this algorithm. Hope it was clear enough.
Yeah.
Any other questions, anyone?
And why do we need it? Like, because we want to reduce the features, because we can't work with a lot of
okay, first part of why we use PCA is to make it less calculation, because don't forget calculation time, it always costs money. So if you have a lot of features, the model will take more time, first of all. Second of all, is better to understand and visualize sometimes the data with less dimensions, and it's better for understandings. And it gets, this is the main part why we use PCA.
Yeah, it's PCA. It's a mathematical way to quantify how much information is stored within our feature, and then it sort of ranks them, if you know what I mean. So it will, in our example, it was between 10 and 12 features that contained, that could explain 70 to 80% of our whole data set. It's just a mathematical way of doing that. Yeah, you can do it in NumPy, but we've got packages like scikit-learn which can do it for us, but that's all it is. It just looks at each particular feature and try to extract how much information is contained within that in reference to our target variable.
Okay, thank you.
Yeah, I would recommend go on YouTube and search for Josh Strammer or StatQuest. He has a very good visual explanation of PCA. It is technically a linear transformation, means it's kind of like squeezing a high dimensional data into small dimensions, into linear dimensions. And then you can use how much variance you are happy with, means how much, because if we have, for example, in our data, we have 63 features. And if we calculate PCA, we have 63 principal components. And if we calculate the explained variance of all those and cumulatively add them up, what we are going to do is we are going to look at that, let's say 12 features. In our data, I think 12 features were giving us about 80% of the variance. And about 25 features were giving us 95% of the variance. That means if we just take the first 25 principal components, we still have the 95% variance explained by those principal components, and that is a good kind of like we have reduced a lot of the dimension of the data, which means model complexity, running time, and so many different things. But we kind of like are still getting the same evaluations for the model. Means our error is not getting affected as much. Our RMSE values or things like that, they're not getting affected as much, which means using just 25 features, we are getting the same results as we would be getting with the 63 features. So it's kind of like a tool which kind of like compresses the dimensions. Yeah, but StatQuest, search for PCA, it has a very good visual explanations of it.
Yeah, I think I saw it, but it's still not like the calculation part. Like, so do you guys know how to calculate it by mathematically? Like,
I can show you. Yes, I can show you.
Yes,
sorry. That's why I said I was in the same situation as you. And
okay, yeah.
StatQuest, it was a good visual thing, but calculation was very hard. So that's why I would just send you the link. I understood better with the NumPy. It was more 1, 2, 3 step better.
Yeah. Okay. Thank you, sir.
So Ina, one piece of advice. Since now you're already on Slack, so feel free to if you have any questions, feel free to ask in any of the channels, and usually any one of us respond. We try to work as like a one team. All of us just help each other out. So more enough.
Yes. And if go through the resource Tim is sharing with you, means what we are going to do is me and Rich, we are kind of like and everyone in this group, we kind of like take questions, and if you are still not able to understand, then we can cover it maybe in one of the meetings. Okay, so don't worry about it. Just if you just go through the link that Tim is sharing with you, the machine learning mastery, that's my go-to blog as well. I always go to that blog as well for anything related to machine learning. So that's a good resource. Go there and see how Jason Brownlee is calculating using NumPy. And if it's still if there are some confusions, just let us know. We will kind of like just add a section in our next meeting covering the basics of it. Yeah.
Sounds good. Okay, guys.
Thank you very much.
It's getting late, so let's just last minute announcement before we wrap up. Well, I would like to thank all the participants for being so active throughout and just working as one team. It was a great experience working so far with all of you. And very good job by the presenters today. It was a very nice experience. In fact, myself, actually, I'll rewatch today's recording for sure. And I would like to thank our task leads, Salman and Rich, for doing a great job so far. They are being very responsible, and whenever there's a need any participant, they're always there to help them out. So I'm very appreciative for their lead and very well done job so far. And I would like to one small favor. I also like to evaluate myself. Our past evaluations, which I sent out, it was more to ask what participants want, so then we can help our task lead, so then they can change their strategy to help you guys best, which I think they did. And if you guys think so as well, there's a raised hand as a standing ovation. I think that's one way to show that they are doing it, at least for our task leads. Last thing before I wrap up, I'm also gonna, since it's a week break, I'm also gonna send one small eval. I know I at least don't like doing eval. I would really appreciate it. Will be personally for me, very small, like what things you like of me, what you don't, and how you want me to in a part 2. So at least just to better help you guys, because that's my true intention, to make sure use my resources to hopefully you guys get the most out of this experience. So please help me to better serve you as well. So I'm gonna send out one small survey based on to help me on that. And that's it. Yes, I don't see anything. For just to tell, since I think welcome Ina. By the way, Ina will be as our new participant who will be joining us for part 2 officially.
Thank you.
And just to let you guys, remind you guys all, by end of part 2, which will end on August 3, you guys will all get Data Camps' 1-year subscription, as well as Data Quizlet subscription, as well as active participants will be invited into the OMCleaner community. Okay. Any other questions? Anyone last minute? Otherwise, I think we should wrap up now. It's too late.
And a few hours a day. Can you add us?
Sorry?
No, I'm joking that I need a few hours a day.
For sure. Okay, I assume we are good. Thanks everyone, and have a very good day.
Yep.
Bye now.
I'll see you soon. Thanks everyone.
Thank you, guys.
Bye bye.
Thank you.
Bye, everyone.